Welcome back to Kinetics and Reaction Mechanisms on Catalyst University. My name is Kevin Tokoph. Make sure to like this video and subscribe. All right, so we're given this problem. The rate constant for this first order reaction is 0.720 per second at 400 degrees Celsius. How long in seconds would it take for the concentration of A to decrease from 0.78 molar to 0.39 molar? Again, very much like the previous video, where we did this for a second order reaction, I'm going to start with the assumption that you're in physical chemistry. This video will be applicable for more than that, and if you want to avoid the integral calculus and differential equations required to get the integrated rate law, then I'm going to tell you, I told you at the beginning of this video, what time to skip to if you're just concerned with solving the problem. But I'm going to do this for multiple classes. All right, so this is a first order reaction, and A is my reactant. So I'm going to first get the integrated rate law. dA dt is equal to, I have a rate constant times the concentration of A to the first, because it's first order with respect to A. All right, rearranging this equation, I'm going to get 1 over A is equal to minus K times the concentration of A. That's my rate law. Rearranging this, I'm going to get 1 over the concentration of A times dA is equal to minus K dt. This right here is a separable differential equation, so I'm going to integrate both sides. Here from T1, my initial time, to T2, and this one from concentration of A1 to concentration of A2, my final concentration. Now again, just like in the other video, I don't like dealing with power rule integrals right like this. I'm going to rearrange this to where it's a to the minus first dA from concentration of A1 to concentration of A2. All right, now I'm going to integrate this. If I integrate a to the minus first, this is a tough integral if you don't remember what this is. But if you ever integrate a or something to the minus first, that's going to be natural log of A evaluated from A1 to A2. Also remember these concentration things right there. And that's going to be equal to minus K, and T1 to T2, this is going to be T2 minus T1. And this is my rate law. I have not evaluated the left side yet, but when I do that, I'm going to get natural log of the concentration of A2 minus the natural log of the concentration of A1 is equal to minus K. Now a simplifying assumption is I'm going to say that initial time is equal to 0, and if that's the case, I can just say K times delta T. All right? Now, at this point, I feel like I could probably start plugging in numbers. I know that I'm decaying from 0.78 molar to 0.39 molar. All right, and I just have to remember the following. This concentration is my A1, this concentration is my A2 because I'm decaying to that. That's my final concentration. All right, so when I start plugging in numbers, natural log A2 is 0.390 minus the natural log of 0.780, my initial, is equal to minus, notice my rate constant up here, negative 0.720 per second. Also notice one thing, my rate constant isn't negative. You can never have a negative rate constant, but remember there's a negative sign out in front of K delta T. And then this is all multiplied by delta T. All right? And now let's go ahead and figure out what these natural logs are. All right, so with the calculator I have natural log of 0.390. All right? And then I'm going to subtract from that, parenthesis, natural log 0.780. And the value I get is negative 0.693. And this is going to be equal to negative 0.7, make sure it was 72, yeah, negative 0.720 per second. And that's going to be times delta T. Now, I will tell you this at this point. You could hopefully see by now that this negative sign will cancel with this one. If you get something where it's pretty obvious that your delta T will be negative, you did something wrong. You cannot have a negative delta T. You need to go back and make sure you didn't drop a sign. So let's divide this. Negative 0.693 divided by negative 0.720. And I get that delta t in this case is approximately 0.963 seconds. And this is going to be my answer. That's how long it takes to ultimately decay from 0.78 molar to 0.39 molar. Okay? Now, one thing I want to point your attention to. This is a really important result that comes out of this, and it's something that might not be obvious, but if you do enough of these problems, you'll start to see it. Notice when I did these natural logs here on the left side, what number did I get? I want to point your attention to something also that's actually rather interesting here. All right. I want you to notice that this 0.780 is actually twice 0.390. If you take 0.39 and multiply by 2, you're going to get 0.78. In other words, we're actually looking here at 1 half-life. So it's not a coincidence that I got this negative 0.693 here when I did the natural log of on this side. Okay? It turns out that for any time you want to calculate a half-life, so delta t, this is for the half-life, which in this case it has to be because we're going from 0.78 to half of that. We're decaying halfway, so it's a half-life. All I'm going to do is take 0.693 and divide by the rate constant. This is actually going to be the half-life for any first-order reaction. Okay, it's not really important to solving this problem, but I just wanted to bring that up because it's an interesting result that comes out of this. Okay. Also note that if we look at 0.693, this is actually exactly equal to, if you include all the decimal points, the natural log of 2. If you plug natural log of 2 into your calculator, you're going to get exactly this number. All right. So another way of writing this is the half-life for a first-order reaction is going to be natural log of 2 over the rate constant. Okay. Now, they won't always be half-lives, and because they're not always going to be half-lives, in general, you're going to have to use this equation right here. This is how you calculate concentrations or time for any decay for a first-order process. Okay, so hopefully this makes sense. Make sure to like this video and subscribe to the channel for future videos and notifications. Thank you very much.